Hello, it's Ryan. We're going to do our first example on work. This is really probably the only example we'll do that is only about work, but we'll use work throughout the rest of the semester, I guess. In this example, I have me happily dragging our favorite crate full of fruit across a rough, level floor where mu sub k is 0.6. If I drag the crate for 10 meters at a constant velocity, determine the total work that I do on the crate. Determine the net work on the crate as well. So there's really two parts. Usually that'd be an A and a B, but I drew the picture for us. If there wasn't a picture, you ought to draw it. I labeled the displacement, the constant velocity, and the coefficient of friction between the crate and the floor. And I showed that the floor was horizontal with my picture, I guess, as well. Now this is asking us to determine the work done first, the work that Ryan does on the crate. And so what we need to figure out is the force that Ryan is exerting on the crate. And how do we ever analyze forces? Well, of course, we do an FBD. I should have done my knowns and unknowns up here. I guess I'll do that really quick. We know the mass of our crate. Mu sub k is 0.6. We know S is 10 meters. And we know A is 0 because V is constant, right? So we need to do an FBD. And we're going to do an FBD of the crate, even though it's Ryan that's exerting the force. We need to analyze the forces on the crate to figure out how much work Ryan is doing on the crate. And in general, this is some sort of rope here. So what type of force is Ryan exerting on the crate? Well, of course, it's a tension force. So we're going to do an FBD for our crate. There's our crate. And we're going to label all the external forces acting on the crate. Well, our crate has a weight. The crate is in contact with the ground, so there's a normal force, a contact force, and it's always normal to the surface, so it's vertical. And now we said it's a rough surface, so there's a coefficient of friction, which means there's a friction force acting on the crate. If this were the only forces, if these were the only forces acting on the crate, it would have an acceleration. But we know that Ryan is exerting a tension force on the crate, like so, and I drew them the same because we were given that A is 0. So all these forces should equal out. I'm also going to put a coordinate system, like always, and this will allow us to determine what we need. Anytime we do a free body diagram, it should be second nature to sum the forces in both directions. Both A's are 0 in this case, constant velocity. The x direction forces, we have a tension and a friction, and the friction is going to the left, which I labeled negative in my coordinate system, so tension minus friction is 0. That tells us that tension is equal to friction, and friction is always the coefficient of friction times the normal force. So it looks like if we could figure out that normal force, we'll know the tension, and if we know the tension, we could determine ultimately the work done on the crate by Ryan. So some of the forces in the y should give us our normal. We have normal minus weight equal to 0, which tells us the normal is equal to weight, and weight is always mg. So now we can substitute that in. So tension is mu sub k mg. But our problem asked us to determine the work done. Work is always the force that's parallel to the displacement times the displacement. And Ryan is the one exerting the tension force, so we need to figure out what that tension force is equal to. That will be the force in here. So the work done by Ryan on the crate is equal to tension times displacement, and the tension is completely parallel to the displacement, isn't it? So I don't have to worry about the cosine. Another way to think of that is we could have said that work is Fs cosine phi, but this is the angle between F and S, which, isn't that a 0 degree angle? So it'd be the cosine of 0 degrees. And the cosine of 0 degrees is 1. So we end up at the same place. You can think of it however you'd like. That means work is equal to mu sub k mgs. And if you go ahead and calculate that by substituting the values, we would get 1825 Newton meters. So that would be 1825 Newton meters of work done on the crate by Ryan. The other part of the problem asks us for the net work. The total or net work is equal to the net force or the total force dotted with the displacement. But what is the total force on the crate? Well, it's 0, isn't it? The total force is 0. The total force is 0. F equals ma. That means this is 0, and the net work is 0, so the net force is 0, so the net work is 0.